invitation. It's great to be back in Bristol in the sunny weather. So I'm going to talk about quantum cloud computing. You know, you guys have seen quantum in the cloud. Actually, Bristol was one of the first places that put their chips in the cloud ages ago. And then IBM and Rigetti, and guess what? None of them are secure. It's even worse than being not secure. And if you look at the IPM, there is a little tick box that you're saying any intellectual property obtained through the interaction with the IBM belongs to IBM. So while this system, of course, is very nice for interaction for the learning purpose, but once the qubit increase, once you really want to run a business on that, security becomes important. Otherwise, we know what we ended up in the hand of the what's not. So how do we do secure quantum cloud? That's where you need to send, photon into your devices. So these are the techniques that we have had years ago that you can indeed do unconditionally secure quantum cloud computing. You just need to send encryption, and obviously quantum encryption, like the QKD encryption. Then you put your data on those quantum QKD encryption, you send it to your device, the device running it, then everything is fine, your data, your input, your output, nothing will be leaking out. Perfect, and that's exactly the combination of QKD plus teleportation, so it works nice. You can implement it with the photonic device, with 4 qubit, we implemented it, but it's not so special, you don't need to have necessarily a quantum computer which is photonic that they are building in somewhere in California, but it actually can work with any photon matter system. Could it be ion trap, could be NV system, could it be continuous variable, whatever. As long as you can have photon communication, then you're able to achieve this secure quantum cloud. Okay, this is what I've been telling you. In fact, if you're interested, there's a very nice review on this general notion of secure computation by my colleague Joe Fitzsimon that I highly recommend to read. It's a very nice high-level abstract view. But what's new? These are the things I was telling you 3 years ago when I was at BQIT 15, I think. So what's new is that it's hard to come to Bristol and not prove that photons are so important. So I'm here to prove to you that these can be achieved only with photons. I want to present to you a result that we proved a year ago on the impossibility of secure quantum cloud without photon. So it might look like that I'm going to talk about quantum complexity and polynomial hierarchy and etc. in a couple of slides, but don't be fooled. It's about quantum optics. Okay, so let's make sure we are in the same page. So we have a client, and what this client, like us, wants to do, so they have some input, they want to compute some output, they have a classical computer, this BQIT is a classical machine, that's what we have. And this function happened to be not in a classical computer, it's Shor's factoring, is quantum machine learning, is quantum boson sampling, it's quantum simulation, whatever you want to think of it. So it's something that you cannot give it to your classical computer and get the data. And here comes some black box server, wherever they could be, whatever system they have, and they say, I can compute anything for you. So give me your data, and I will compute it, and I give you the result of your sample, the result of cracking whichever code you want to crack. I will do the database search. And of course, you want to say no. No, thank you very much. I don't want to send my data. So how you want to interact with this machine is that, can I encrypt this message, in a very nice way, and then I send my encryption to this server. And ideally, I want this encryption to be super encryption. I don't want one of these post-quantum dodgy things. I want to make sure that my encryption does not leak anything but the size. It needs to leak something. We can prove theoretically that you need to leak something, because I need to say what's the size of my computation. Otherwise, it's like, okay, you can even give an upper bound. But if you want to have information security, means the only leakage that you're giving is the bound of the size of your data. This is the question that I know. I give you encryption. I'm even happy to go back and forth. So there is this notion of fully homomorphic encryption that you don't want to have interaction, but that's not even the purpose here. I'm happy, just want to be giving you an encryption of my data and talk to you afterward, classically back and forth, and to see that whether you can do the computation. So this is what the setting are, and just in order to be fun, we change the name. It's essentially classical block computing or classical cloud, etc., whatever you want to call it. But this notion was defined even before, and it's called generalized encryption scheme. that I encrypt something, I give this function to some remote superpower oracle who can solve my problem, and then I want to make sure that nothing is leaked. Okay, so there's a very nice old result by Abadi et al. That they look at this thing. So what kind of function can have such a wonderful property that I encrypt, I send it away, somebody compute, give me the output, nothing is leaked. Okay, this is the question that they asked. And they showed, okay, this is complexity, but we parse it. So they showed that it is not the case that a lot of problem can be done like that. So if you look at the classical function, of course, for a very simple classical BPP concept, I don't even need to talk to a server. I just compute it, so no problem. But it's a little bit bigger than that. And this bigger than that is the class of MP given the advising polynomial intersection with MP given a polynomial. It means that there is some non-trivial things that you can do. And interestingly enough, for example, in that class that you can achieve such things, there's discrete logarithm. So if you want to calculate your discrete logarithm using this sort of powerful remote server, you can. But if you want to do it with factoring, you can't. So these are the very funny results that was already there. And then more strong no-go results. So they're like, is it really the case that I can have some sort of powerful oracle for MP problem? All of these problems that we are interested, all of these traveling salesman, satisfactory, all of these things that we want to solving, they show that in fact no NP complete problem could be solved like this. You cannot push the hardness to somebody else. So unless polynomial hierarchy collapse. And that means no goes on. It's like no signaling for us, okay? This is like you cannot have polynomial hierarchy collapse. So the summary of this blah blah is that in classical, we know that it is not possible to use this classical encryption in this very information theoretical secure for a very large class of problem. Okay, so it's very powerful. Usually, you don't have this sort of connection between cryptography and complexity so concretely. So now we want to ask exactly the same question in order to prove photons are very important. So like, can you achieve such a, again, the classical computation? So this is this scheme. Does BQP means that bonded quantum polynomial, essentially your quantum computer. So could it be the case that now I have this function, remember it's quantum machine learning, quantum simulation, quantum factoring, etc. Can I give it to a client and I come up with some sort of nice encryption of my message? After all, I'm like encrypting which code I want to crack, and then send it to a server, and server doesn't learn anything apart from the size of my encryption and give the result back to me, and I want to have this information theoretical result, which exactly means, as I say, can we do secure quantum cloud without photon? Okay, so that's the question. Everybody happy with the question? So now the answer is no. It turns out, that we give strong evidence that the answer is no. And it's very, so like in the classical context, the evidence was very strong. If you remember, I said that if you could have done that, for example, for NP complete problem, polynomial hierarchy collapse, so that's a very, very strong evidence. It's the end of the game. But if you follow the couple of slides that I want to show you, that it's not really end of the game. We don't have as strong result that it's really polynomial hierarchy collapse. It's relative to Oracle polynomial hierarchy collapse. And for those of you who are familiar with the Oracle complexity, sort of like we want to strengthen it further. And there is another result regarding the sampling that is stronger. So, but it is good enough. It's for photonic people, it should be strong enough. That we are on the good side. We need photon to be sent. So essentially, we are proving that there are problems that quantum computer can do faster, better than classical, and we do not have an information securely way of delegating into the cloud if we want to have classical encryption. Remember, we have a solution if you are happy to do quantum encryption of your data. We just want to see that this is optimal. Okay? So let's, you can switch off if you want. And I'm just going to give a couple of slides to show you the flavor of the way that we're proving this theorem, and then we come back again. So we want to see that can we develop a generic, generalized encryption scheme for any problem in the BQP. So the methodology that is very similar to the Abadi methodology that was defined for the classical. So what you do, essentially you can see that if the server is supposed to learn nothing about this computation, this interaction back and forth is like he wants to solve this hard problem, MP problem or BQP problem, etc., given some advice. So this back and forth classical string that we're sending, getting the outcome, whatever it is, it's like a polynomial advice in these complexity classes with the polynomial as well. So here's where the problem comes for like making our result not as strong as we want, is that the way we could have proved, we needed to fix the size of this advice to be of dimension D, is not as arbitrary one, so we need to define this generalized encryption scheme with some sort of fixed parameter, and as a result it's become oracle. So we are defining an oracle, means that we are assuming something is hard, in a simple word, and that thing is hard, then we can prove relative to the oracle, indeed there are problems sitting here that you cannot encrypt them without photon. I told you it's about photon. So this oracle is based on the Simon problem. Those of you know is that essentially you're cooking up. This is like a classic way that we prove in this complexity. You figure out the function that we know is very hard to be solving it, and then if that's the case, if that's thing given me as oracle, then I can put it in that separation. Okay, so you can go to it. And then maybe another result that to show this evidence of why this is so hard, is like it's making more clear. Let's go to the sampling. We all love boson sampling, and these are a problem that indeed quantum computer can do better than classical computer. So thanks to this strong impossibility result that exists, that we know that no classical computer can, in the exact setting, sample from the boson sampling. So you might want to have, in an encryption, because boson sampling is so important, you want to make sure that the server does not know which boson sampling is sampled from. This was a joke. Okay, so essentially what you're doing, so you want to make sure that you're giving the description of a linear optic setting to the server, and you're asking the server to create that sample, and you get the sample, but you want the server does not know which linear optic server you take it from. But these are, of course, there is more general problem to say, but just to give you, because of the separation we have, then it's very easy to show that indeed it is not possible to securely do boson sampling. So that's very concrete way of saying, if you want to do boson sampling and you want to hide it, you have to send your photon in and you have to get photon back. And this way again is not collapse of polynomial hierarchy, but it is a bunch of things that is essentially say that if we could have do a secure way of running boson sampling on a remote quantum server by classical encryption back and forth, then somehow we can construct an efficient circuit for solving permanent, which we know that is very hard problem because it's complete for sharping. So again, that sort of complexity assumption. So where we're standing essentially that secure quantum cloud is single qubit quantum client. Very happy, yeah? So we can go home. I made all of you quantum optics people friend with me, and the point is that I want to also be friends with superconducting people. They kind of have more money. So what should we do? So now I want to show you on the possibility of doing secure quantum cloud without photon. Actually, it is possible. So this is another recent work that we put up, and it's about delegated pseudo-secret random qubit generator that I talk about. So here I'm actually kind of saying something that I say impossible. So what's the catch? Is that of course I can reduce my requirement on the security. Before I wanted to have information security, nothing to be leaked, and that's done, is in the pocket, killer app. If you want to have unconditional secure cloud, you need to have photonic. But if you want to deal with the server back to this thing, so this is indeed, we need to send this photon, but if I want to put that magnificent piece of chip there, which is sitting in a fridge, and you cannot set a photon in or come out of it in the room temperature. I know eventually there might be in the link, but if you want to do that, then I need to do something about this qubit. Something about this randomized QKD qubit that I said are so essential to be sending it there. So I need to somehow securely, classically emulate that procedure. That's the moment that you would say, of course it's impossible, otherwise you could have done QKD classically. So we know that it's not possible to achieve. So what I'm going to show you is that if you're happy to have now that wonderful post-quantum algorithm that I was saying about is how important they are, so we can use those to make sure to do classically secure quantum cloud computing. Everybody's with me? So we're happy about the transition from photon to no photon? Dephotonization, essentially. Okay, so the whole procedure that I'm going to present in the next couple of slides, that we know that for this quantum cloud, the only thing I need to send is this single qubit, this red dot, are nothing but QKD state. Okay, they are just for a state that they are in the unbiased spaces, they are plus minus 0, 1, or whatever other encoding you want. So how could I make, using a classical client, which is coding, to run and create this remotely this state and achieve a level of security? Okay, so you need to create a sort of post-quantum. So this is the way. We're back to this wonderful classical iPad that is supposed to write the code and to run it over the chips. So what we are starting with, we're selling, we're giving the classical instructions. So us giving the code classically over the cloud with our mobile phone to the Google to please prepare this general superposition. They can definitely do. Okay, nothing is leaked. Then I'm starting asking them a function that I'm going to define in a second what that function is, maybe actually right now. So it's a very special trapdoor classical function. This trapdoor function, it is a function that is easy to compute forward, is very hard to invert. But if you have a trapdoor, you can invert it. So we'll see a little bit about that. So that function is public. I can tell to the server that this is the function that I'm using for creation of my key and etc. Please create this superposition. You have a magnificent quantum computer, it could be photon or whatever. Please apply this function that I'm sending you also classically the instruction about it to create that superposition. So what are the properties of that function? I'm going to tell you in a second, but after the server prepared this thing, you ask him, okay, now that you prepare, please measure the second register. So this function is here, have this particular property. It is too regular, means that every fx that you look at has two possible elements corresponding to that. F of x1 is equal to f of x2 for any random y that is coming out of the image. And it is collision resistant, means that it's very hard, if you know the image, to calculate the pre-image of that function. So if I look at when the server has measured this thing, he knows which image, which f of x he collapses, is randomized, but he will see which y he has collapsed to. But it is the property of my classical function that it is hard out of the y you get up. This is exactly the concept of hashing and everything that is used for all the classical crypto set. And it also, on top of that, is post-quantum secure. It means some sort of lattice space learning with Edinburgh, etc., that even my quantum computer cannot invert it. So this magical box exists. There is a couple of them. There is a very recent paper, again, is about how to use such function to calculate a certifiable random number generator by Thomas Vidic et al. So this function is there. So we use those functions to create this pre-image. So far you can say that, okay, fine. You kind of see I created a qubit, that the description of this qubit is not quite known. It's like two random state x1 and x2. How could I use this superposition that me, the classical client, has some knowledge about it because I know what is the trapdoor, but the server does not have any knowledge about it? Well, you do a little bit of cooking around, so you create lots of those qubits. Okay, lots of those. It turns out, depending on some property of this trapdoor function, some of them remain entangled when the server measuring, some of them are not entangled. And the connectivity are unknown. Because of the property of trapdoor, which is unknown to the server, the connectivity is unknown. So this is exactly the view that the client will have about the general state over the server, whereas the server does not know all the details. And then somehow you squeeze, so you squeeze the uncertainty that is over all of this qubit to one possible place, and that possible place exactly gives me the randomness that I needed. So you make a measure, you're instructing the server make a measurement, so he's seeing them, but he doesn't know which of the one that they are contributing, which are the one that is rotating. So it's exactly like a hidden noise that I'm introducing to this state, and behold, at the end you get this little state, which are exactly like QKD state, that there is a rotation over this QK state, but this theta, which is exactly which rotation has been applied over this plus state, is unknown to the server, because it depends on this x1, x2i, that was the pre-image that we say that client server could not calculate. Okay, so let's wrap up. So I pick up this magical box F that is hard to calculate the pre-image given a y. The server is making a measurement, give me the y. Out of that, I can calculate this formula. I can plug in all the missing elements in here. But as long as the server, this lattice-based crypto post-quantum is secure, cannot be cracked down by a quantum server, then this theta is become only known to me, so I'm back in the business. So I have created remotely a bunch of state that I know the description of them, but the server doesn't know. So this doesn't violate QKD because, of course, my computation has become computationally secure. So it's useless for driving a secret key, because if I wanted to do post-quantum, why even bother to go through this mechanism? I just would do public key post-quantum. But it's useful for the class of problem that I'm going to define, where I'm happy to have computational security. So this is the cost when I go from information security to the computational security. So indeed, the picture of secure cloud is that either you do it with Photon, and you're very happy you have information security, but if you want to do it because you want to run it on a superconducting, or if you want a bunch of other applications that if I have time, my chair is sitting, so it means that I have plenty of that. So, then you're happy to have computational security. Then you're bringing this gadget that I was presenting. It's a good time to ask questions before I move on to the application.
I don't understand how you know all of the information that the server doesn't, because if it's hard to find the pre-images, how do you know the other pre-image that you haven't sent to the server? Okay, so this is because of the trapdoor. So these are all the magical things that exist in the classical part. So this function, thinks of it, what is the best example of trapdoor on top of my, so essentially I have the secret that allow me to invert the function. So when we are in here, what was the? If there's a limited number of these functions, surely a malicious person could just tell the server these are all the functions, and then the trapdoors will come up. Yes. So this part that I'm putting it here is assuming they are secure. So I'm assuming there exists a security which is proven up to the assumption of the randomness that is there. The important is that answering the question of how do I know what this x1 and x2 it is that because this f of x is exactly the image of this x1 and x2. So now, you might ask in the question, and I'm answering the question differently, what if the server lied to me that which y I obtained? And then I would not calculate the correct image corresponding to that. And that's the other question, that we need to impose some sort of honest but curious behavior, and I need to introduce another machinery to make sure that the server actually tells me the correct measurement. But let's be in a semi-malicious scenario that the server prepare this superposition, make a measurement of this thing, then we know exactly that this superposition on the first qubit is x1 plus x2, where x1, x2, f inverse of f of x, and this gadget that I'm picking up off the shelf is telling me if you give me f of x, I can always run f inverse of x, because I know these secret parameters. I mean, all of them has a key k that is omitted there. Then I know those k, so I know which of those functions I've picked up, so hence I can invert, but nobody else can invert. Yes?
Is there an excess computational overhead on the computer side of it? And
sure.
How does the overhead compare to how secure the thing becomes?
Okay, so the overhead is exactly about this piece, but look, these are fresh from the oven. These are like 2 weeks ago results. So we have a lot of work that we're trying to do to make them efficient. Maybe there is some efficiency. So I was at the first overhead, even before going to the classical overhead, even quantum overhead. We were using like 100 qubits to get one of those qubits. So still photon is good, because the most practical way of doing secure cloud is actually send my QKD state, and you can right away use them for the key. Whereas if I want to do classical this thing, I need to go around and I use many of this qubit to get this thing. But well, you never know. Maybe there's a 1,000 cluster state, whatever, superconducting. So there is overhead in the qubit creation. They are all polynomial, so they are all efficient, but they are badly polynomial to some extent. The other overhead is on the classical part. All of this lattice space, etc., they also have a huge overhead. And that's why there is several candidates. And again, it's a very active research that people trying to, for the sake of this NIST competition that Christoph was mentioning, that people are actively trying to make them more and more practical and have a better overhead and more realistic part. So these are all work in progress and need to make them practical. So that's a good point. Okay. So now that we realize what's the cost, ooh la la, okay, so now you're standing. Okay, we can call it a day. So essentially the perspective is that back to the same slide that Christoph put out there. So now we're going to have this hybrid. Something is using satellite, something is using classical, something is using quantum communication. Some places we cannot use quantum communication, but what the message that I'm trying to show that like with all these various gadgets, with their cost taken into account, we can make them all secure. We're no longer going to be in the Facebook area. Everything is secure. So maybe I just want to mention one quick application to jump over this thing. Is about verification, because verification is a question that even forget about the future application. We want to deal with the verification of superconducting devices. Superconducting devices, when you go to the 100 qubit, you know that all of this supremacy, etc., we don't have a certification of it. And all of the method that we have been proposing before for verification, this computational limited, which again I was talking about before, is always very good. They're very practical, sublinear, lots of people have worked on it, but it requires again this photon communication. And you cannot send photon into the D-Wave machine or Google machine or etc. So here is a particular place that you don't care about overhead, you don't care about cost, you want to have classical verification of it. And indeed, this methodology that we have, that we use our crypto system of sending this qubit inside the system to be able to hide what computation is doing, to reduce general deviation to the particular simple deviation so I can detect this thing. It was, now you can use this secure classical computation. There is a very recent result that appeared in the archive beside our own work, which is precisely solve the problem that for the first time we can have classical client verification of quantum computer, which is post-quantum secure. So that's very exciting because despite the overhead, you can do that. So I need to thank my team, which make all of these wonderful works, as well as all the collaborators of it. So thank you very much.
Perfect.
Photonization.
Photonization.
I'm not sure I like that term. All right, time for one question.
So it seems that the server has the other register which has the information you want to keep hidden. So
Yes.
why can't the server just measure it?
So server can measure, server exactly know the Y, the image function.
No, I mean the other register, the X.
The X1, because it's a superposition.
Yeah.
So this way, so this is a very good question. So the server has X1 plus X2, and he can have exactly the best information that he can do, but you can analyze that he cannot have full information about both X1 and X2.
Okay.
He can, for example, get the AND of X1 and X2. And that magical formula, which was there and is gone, is a way that if you have all the information X1, but nothing about X2, you're missing. If you have all the information about X2, but everything was missing. And if you have the AND of them, still you're missing. So the formula is written in such a way, that's the squeezing part, that you need to have both full information of X1 and both information of X2 to do that. And Mollaba bound exactly forbid you to have the full information out of the superposition instead.
Right, we can thank Elham again.